This is section 2 of the kinematics lab, and for this part of the lab, the displacement between the two photo gates is going to change. Now for this part of the lab, we are only going to be using the metal marble from here on out. For all of section 2 of the kinematics lab, the angle of the ramp is going to be 15.2 degrees. That's not going to change. At station 1, the displacement between the two photo gates is going to be 0.10 meters. We're going to run 3 time trials with the metal marble. We're going to have the same setup where I put the ruler there. We're going to put the metal marble just above that, and we're going to run 3 time trials. So this is time trial. So this is station 1, time trial 1. This is time trial 2. This is time trial 3. At station 2, the displacement between the two photo gates is 0.20 meters. This is time trial 1 for station 2. This is time trial 2. This is time trial 3. At station 3, the displacement between the two photo gates is 0.30 meters. This is time trial 1 for station 3. This is time trial 2. This is time trial 3. At station 4, the displacement between the two photo gates is 0.40 meters. This is time trial 1 for station 4. This is time trial 2. This is time trial 3. At station 5, the displacement between the two photo gates is 0.50 meters. This is time trial 1 for station 5. This is time trial 2. This is time trial 3. At station 6, the displacement between the two photo gates is 0.60 meters. This is time trial 1 for station 6. This is time trial 2. This is time trial 3. At station 7, the displacement between the two photo gates is 0.70 meters. This is time trial 1 for station 7. This is time trial 2. This is time trial 3.
All right, these are the Kinematics Labs calculations. This is part 2, displacement versus velocity. All right, so in this one, this is the data that I got when doing this. Now, if you do this lab, this is very similar to the data you should get. So the angle is at 15.2 degrees, and notice we did 3 time trials, and this was my average time, and the displacement was set. Now we're going to calculate the acceleration and velocity. Now this one's going to be a little bit different because there is a systematic error that we have to take into account. So let's just look at those kinematic equations. These are the variables, and we know 3 of them that were given to us through like measurements, and then we're going to calculate the other 2. So remember, when we're doing calculations, always ask yourself 3 questions. Number 1, which variable are you being asked to find? Number 2, what 3 variables do you already know? And number 3, which equation has those 4 variables? So let's go ahead and look at station 7. Now we need to look at station 7 first because there is that systematic error that is worse the closer those photo gates are apart. So we're going to go with the best case scenario. So a marble starts from rest and accelerates uniformly over a time of 0.7949 seconds for a displacement of 0.700 meters. Determine the acceleration of the marble during the time interval, then calculate the velocity of the marble at the end of that time interval. So let's ask ourselves that first question. What's the first thing this is asking us to find? It's asking us to find that acceleration. So then we need to see what the 3 variables that we know. So we know these 3 variables. We know it starts at rest, the initial velocity. We know the time interval, delta t, that was given to us by the average of the 3 time trials that we took. And we know delta x, the displacement, that's the distance in between those photo gates. That was set on the ramp, so 0.700 meters. So I just go ahead and write them down just so I can keep track of them. Now I'm looking for the equation that has these 4 variables, or I can take a shortcut and look for the one that does not have final velocity. I'm not concerned with that one yet. And it's the second one. So now this is just an algebraic problem. I just plug everything that I know. Now 0 times, since the initial velocity is 0, I don't have to worry about that term. That term is 0, but just solve for the unknown, which happens to be the acceleration. And when you plug all these numbers in, this is what the acceleration is, 2.22 meters per second squared. Well, now that I know that, I can find the final velocity, the velocity at that photo gate. I can use any of these equations, but I'm going to use the third one, because if I calculated the acceleration incorrectly, I won't get the final velocity correct. But in that third one, I am able to be sure, just to double check. So I'm going to plug everything that I know into that equation and solve for the final velocity. And I get 1.76 meters per second. Now notice when I was calculating, my answers have 3 significant figures. And that's because that's the least amount of significant figures in my problem. My answer when calculating can only be as accurate as my least accurate instrument, what happens to be 3 significant figures. All right, so now what I want you to see is that we just did station 7. So that was when those photo gates were the farthest apart. We're going to use that acceleration for all of these calculations, and I'll tell you why. Because if we look at let's just use this and we'll calculate station 1. So same thing. We're going to calculate the velocity of the marble at the end of the time interval because we know the acceleration already, right? So we just calculated that at station 7 because the acceleration is going to be the same the whole way down. So now I'm going to use this top equation because it's easier, right? So I'm just going to plug everything that I know, and all I have to do is multiply the acceleration by that time interval, the average time interval at that station. And I'm going to get 0.525 meters per second. So using that acceleration that I calculated in on station 7, I'm able to calculate the velocity at every single point. So I can go ahead and just do that all the way down. Now, this is why we need to use the acceleration at station 7, is because I calculated the acceleration with the data that we were given, and, well, that's the graph up there, up at the top. Now, notice the acceleration looks like it's decreasing as it rolls down the ramp. Well, the ramp is a straight line. The acceleration should be the same. The velocity is changing, but notice what happens. It's gradually decreasing as those photo gates get far apart, and it's not a linear curve. It looks like it's approaching a certain number. So what this is that there is a small systematic error, and it's because we don't start the marble exactly where that photo gate starts. We started it about a centimeter before because we used like a ruler to make sure we started it at the same time. So that little error had a large effect when those photo gates were really close to each other, but as the photo gates got farther and farther apart, that systematic error became less and less. So we know that the most accurate acceleration is going to be the one with the one with the photo gates that are the farthest apart, which is station 7. So we're just going to use 2.22 for the acceleration, and then we're going to use that to calculate it. So that way, if you look at the graph below, our velocity versus time graph should be a straight line, and that slope should be 2.22 meters per second squared. The acceleration will be the same. All right. So once again, this is the kinematics part 2, calculations.